Chapter 11. Pipe Data.
Next, we turn to pipe data basics.
This slide covers the pipe thread engagement length and piping data standards required to achieve a leak-free joint. The thread engagement length, dimension A, is the sum of the hand-tight engagement length L1 and the wrench makeup length L3. For example, it is defined by size such as 0.27 inches, 4/1/8 inch, and 0.53 inches, 4/2 an inch. Other detailed values are based on standard specifications such as ASME B1.20.1 and B36.10M, so please first verify the nominal pipe size, material, and schedule grade, such as STD or XS, of your piping design before referring to the necessary values.
Let me walk you through the column configuration of the pipe data table. On the left is the identification column, followed by the nominal pipe size in inches. Next is the wall thickness column, where wall thickness is denoted by the variable symbol T. This T value serves as the reference dimension for calculating the metal cross-sectional area and pipe weight, which we will cover later. The identification column lists both iron pipe size schedule numbers and stainless steel schedule numbers together.
This table is a reference showing the schedule number system and standards for stainless steel. To distinguish it from carbon steel, an S is added after the schedule number for stainless steel, denoted as 5S or 40S, for example. Since carbon steel schedules and stainless steel, S, schedules are listed side by side for the same nominal size, please clearly verify the difference between the two specifications during design. Both outside diameter and wall thickness are expressed in inches, and I recommend directly locating the necessary values based on the ASME B36.19M standard.
This table is a reference summarizing the actual outside diameters and wall thicknesses by schedule for small bore piping from 1/8 in to 1/2 an inch. In particular, it demonstrates the principle that for the same nominal size, standard corresponds to 40S and extra strong corresponds to 80S in terms of thickness. For example, for 1/4 in, 10S is 0.065 inches, and standard/40S is 0.088 inches. Rather than memorizing all the values, please first verify the nominal size during design and then find and apply the wall thickness T value for the required schedule.
The right-hand column group of the table contains area and weight information. The transverse internal area represents the cross-sectional area inside the pipe where the fluid flows, and the pipe weight shows the weight of the steel pipe per foot in lb/foot. The area of metal is the cross-sectional area occupied by the pipe wall, essentially the area of the metal part. Area values are expressed in square inches, and all are calculated from the wall thickness T and outside diameter seen previously.
This section defines the inside diameter column, along with the fact that the area of metal is in square inches. The inside diameter is denoted by the variable symbol D, and the inside diameter D is equal to the outside diameter minus twice the wall thickness T. This D value is the reference dimension used to calculate the flow cross-sectional area and flow velocity. It is helpful to remember the relationship that for the same nominal size, as the schedule number increases, the wall thickness T becomes thicker, and consequently, the inside diameter D becomes smaller.
This table contains inside diameter, cross-sectional area, and weight data according to the nominal size and schedule of the pipe, showing the correlation where the inside diameter decreases and weight increases as the pipe thickness increases. For example, in the 1/8 in section, the inside diameter decreases from 0.307 inches to 0.215 inches. As the schedule gets thicker, and in the 1/2 an inch section, the pipe weight increases from 0.54 pounds per feet to 1.71 pounds per feet. Please note that the fluid cross-sectional area is distinguished and listed as small, in square inches, and large, in square feet. Please refer to the detailed values according to your design conditions, verifying the nominal size and schedule first before extracting the necessary physical quantities.
This slide defines the sources and notation conventions that ensure the reliability of the pipe data table. For instance, wall thickness and weight data follow the ASME B36.10M and B36.19M standards, and abbreviations such as STD and XS refer to standard and extra strong thicknesses, respectively. Especially for stainless steel, please check the schedule numbers with an S after the number, such as 40S or 80S. Since this table is a reference where the same conventions apply across all nominal size ranges, I recommend directly locating the necessary values according to the material and schedule number of the piping you're designing.
I would like to introduce the nominal pipe size and wall thickness columns within the header structure of the table. Below the identification area at the top, the nominal pipe size column is placed in inches, followed by the wall thickness column. Wall thickness is denoted by the variable symbol T, and the unit is inches. To fit multiple nominal size groups side by side on one page, the nominal pipe size column is repeated twice. Wall thickness T is the basic dimension corresponding to the outside diameter minus the inside diameter D divided by 2, and depending on this T value, the standard STD, extra strong, XS, double extra strong, XXS, and each schedule number are determined.
This chunk introduces the definition of the variable symbol for the wall thickness column. The values in the wall thickness column of the table are identified by the variable symbol T, and the unit is inches. The T value is given differently for each schedule, from standard, STD, extra strong, and double extra strong, to 5S through 80S. For the same nominal size, as T increases, the inside diameter D decreases, and the cross-sectional area occupied by the metal increases. Ultimately, wall thickness T is the most critical dimension that determines the pipe's own weight and pressure rating, namely the schedule.
The following chunk introduces the table structure, where the wall thickness column is paired and repeated with the nominal pipe size. The nominal pipe size column and the wall thickness column are grouped as a pair and repeated several times within the table. The symbols in the data body are all identically T, and the unit is inches. The reason for arranging the nominal size and wall thickness pairs in multiple columns is to compress several nominal size blocks onto one page. Within each nominal size block, the T values for standard, extra strong, double extra strong, and stainless steel schedules from 5S to 80S are listed in order.
This table shows the fixed dimensions of the outside diameter according to the nominal size. The core principle of the outside diameter is that it remains constant regardless of the schedule within the same nominal size. For example, 1/8 inch is fixed at 0.405 inches, and 1/2 inch is fixed at 0.840 inches. Therefore, even if the wall thickness T changes according to the schedule, the outside diameter remains unchanged, and instead, the inside diameter D varies. Please verify the detailed values directly from the table and use them as reference dimensions when matching connection specifications such as flanges or fittings.
I'd like to introduce the outside diameter column of the piping data tables in Chapter 11 of the Fisher Handbook. In the table, the outside diameter column is expressed in inches, and for the same nominal pipe size, the outside diameter remains constant regardless of the schedule number or wall thickness. This is the core principle of piping standards. By fixing the outside diameter, increasing the wall thickness T results in a decrease in the inside diameter D. The reference standards for the entire table are ASME B1.20.1 for carbon and alloy steel, and B1.36.19 for stainless steel. The columns are arranged in the order of identification, schedule number, outside diameter, wall thickness, transverse internal area, and weight.
This slide is a reference table summarizing the outside diameter and wall thickness data for major nominal sizes, from 3/4 in to 1¼ inches. For example, the outside diameter of a 3/4 inch pipe is 1.050 inches, and the wall thickness varies from 0.065 to 0.308 inches. For stainless steel, these are categorized by schedules such as 5S or 80S, while for carbon steel, identification symbols like STD or XXS are used. Since not all values are listed here, please first verify the nominal size and material of the piping you are designing, and then refer directly to the corresponding wall thickness value.
I'll now introduce the transverse internal area and area of metal columns in the table. The transverse internal area refers to the cross-sectional area where the fluid actually flows inside the pipe, This is the base value used to evaluate flow capacity via the inside diameter, d, during valve sizing. Meanwhile, the area of metal is the cross-sectional area of the pipe wall itself, which increases as the wall thickness, T, increases and is directly proportional to the pipe weight per unit length. Adding these two areas equals the total cross-sectional area based on the outside diameter. Therefore, you can see in the table that for the same outside diameter as the schedule increases, the area of metal increases, and the internal area decreases.
Although these are the same area column headers, I want to explain the distinction in units here. The internal area and area of metal are basically expressed in square inches. However, the table also includes values expressed in square feet. This square foot value is identical to the volume per foot of pipe length. In other words, cubic feet per foot. That is why the table lists the uppercase item in square feet and the lowercase item in square inches side by side. The volume conversion is simple. Multiplying the square foot value of the internal area by the length in feet gives the internal volume in cubic feet. Thanks to this dual notation, flow rate, internal volume, and weight calculations can all be handled in a single table.
I'll explain how the area of metal column leads to weight calculations. The area of metal, combined with the specific gravity of steel, serves as the basis for calculating the pipe's own weight per unit length, which is listed as pounds per foot in the table. There are two types of weights in the table: the weight pipe, which is the weight of the pipe itself, and the water weight, which is the weight of the water filling the pipe. As the wall becomes thicker and the area of metal increases, the pipe weight increases, while the water weight decreases because the internal area is reduced. These two weight values are used directly in piping support design and load calculations.
I'd like to discuss the relationship between the inside diameter and water weight. The inside diameter d is the value obtained by subtracting the wall thickness twice from the outside diameter, calculated as d equals OD2T. This inside diameter d is the most critical input for valve and flow calculations, and it is used as the pipe diameter reference during CV sizing. The water weight, expressed in pounds per foot, is the weight per unit length when the internal volume based on this inside diameter is filled with water. As the schedule increases, the wall thickness T increases, which reduces the inside diameter d, and consequently, the internal area and water weight also decrease. Therefore, even for the same nominal pipe, you can immediately compare how the effective flow area changes just by looking at the change in inside diameter d.
The inside diameter item in the piping data table defines the dimension of the actual path where the fluid flows, and it is determined by subtracting twice the wall thickness from the outside diameter. For example, even for the same nominal diameter, if the schedule number increases, the wall thickness, T, increases, causing the inside diameter, d, to decrease. Therefore, engineers should first verify the nominal diameter and schedule number of the piping they are designing, find the corresponding d value, and use it as the reference dimension for calculating cross-sectional area, flow velocity, and CV. Since this table is based on the ASME B.20.1 and B.20.1 standards, I recommend verifying the applicable standard to refer to the correct dimensions.
Now, I'll introduce the column configuration where the water weight and inside diameter items are placed together. The water weight indicated in the header refers to the weight of the water contained in 1 foot of piping, with the unit being pounds per foot. This water weight is proportional to the internal cross-sectional area of the pipe, so it is determined by the square of the inside diameter. Within the same table, the inside diameter d is presented in inches as a pair with this water weight. Water weight is separate from the pipe's own dead weight and is used to calculate the load when the pipe is completely filled with water. All these values are extracted from ASME B.20.1 and B.20.1 data.
This table is a numerical data table for piping in the range of 1 inch to 1.5 inches, nominal diameter, showing changes in physical properties according to schedule changes. For example, as the schedule increases, the inside diameter d decreases from 0.920 to 0.434 inches, while the pipe weight tends to increase from 0.69 to 2.44 pounds per foot. In particular, please note during calculation that the cross-sectional area, A in square feet, is identical to the volume in cubic feet per foot of pipe. Please refer directly to the table according to your design conditions and reflect the correlation between the decrease in cross-sectional area and the increase in dead weight as the schedule increases in your design.
This section covers the sources and notation conventions for the piping data table. The table covers carbon steel, alloy steel, and stainless steel piping. The identification information, wall thickness, and weight values listed are extracted from the ASME B.20.1 and B.20.19 standards. To summarize the abbreviations, STD stands for standard, XS for extra strong, and XXS for double extra strong pipe. Also, remember that the transverse internal area value expressed in square feet is exactly the same as the volume in cubic feet per foot of pipe. This chunk indicates that the table is a continuous section that carries over to the next page.
Next, we turn to pipe data analysis.
This chunk contains the header items of the piping data table, and I'll introduce the identification, nominal diameter, and wall thickness. The nominal diameter is expressed in inches and is the reference item that distinguishes each row of the table. The wall thickness T is also in inches and is a key dimension determined by the schedule number. The identification column includes the notations STD, XS, and XXS, along with the schedule number. Even for the same nominal diameter, if the wall thickness T increases, the inside diameter D decreases. This wall thickness T, along with the outside diameter, is the basis for calculating the inside diameter, cross-sectional area, and internal pressure strength.
This item introduces the wall thickness column, or wall thickness T, of the piping data table. The T indicated in the header refers to the thickness of the pipe wall in inches and is defined by the schedule number. Regarding the relationship with the inside diameter, D equals OD2T, meaning the inside diameter is found by subtracting the wall thickness of both sides from the outside diameter. Therefore, as T increases, the cross-sectional area and inside diameter D decrease, and the pipe weight increases. For the same nominal diameter, XS is thicker than STD, and XXS is thicker than XS. All these values are extracted from the ASME B.20.1 and B.20.19 standards.
This slide covers the nominal pipe size and wall thickness columns from the pipe data table on page 251, showing the standard dimension system according to ASME B.30.10 and B.30.19. For example, if the nominal pipe size is 1/8 inch, the wall thickness T value is defined differently depending on the selected schedule. The remaining detailed figures are organized so that engineers can refer to them directly based on their design conditions. Therefore, please first verify the material and nominal size of the pipe you need. Then find the wall thickness T value that matches the required pressure rating and apply it to your design.
This slide covers the outside diameter column of the pipe data table, demonstrating the principle that the outside diameter remains constant regardless of the schedule, provided the nominal size is the same. For example, the outside diameter for a 1.5 inches nominal pipe is fixed at 1.9 inches, and for a 2 inches nominal pipe, it is 2.375 inches. Consequently, as the wall thickness increases, the inside diameter and the flow cross-sectional area decrease. Strength ratings such as STD or XS are also configured with different thicknesses based on this same outside diameter. Please refer to the detailed figures for the corresponding nominal size when reviewing dimensional compatibility for accessories such as flanges or valves.
This slide is a reference table summarizing the relationship between the outside diameter, identification system, and schedule number. Basically, it shows the principle that as the schedule number increases for a given outside diameter, the wall thickness T becomes thicker. For example, for a nominal size of 1.5 in, with an outside diameter of 1.9 inches, the wall thickness varies from 0.065 to 0.4 inches. Depending on the schedule, engineers should refer to the remaining detailed figures according to their design conditions. And please note that the internal area values expressed in square feet can be used identically as the volume in cubic feet per foot of pipe length.
This slide contains detailed information for the outside diameter column and the sections for nominal diameters of 1.25 in, 2 inches, and 2.25 in. In the pipe data table, This table shows the correlation between outside diameter and wall thickness, according to the iron pipe size and stainless steel schedule number systems. For example, for a nominal diameter of 1¼ inches, the outside diameter is 1.660 inches, and the wall thickness is determined from 0.065 to 0.400 inches. Depending on the selected schedule number, the remaining figures are organized for engineers to refer to directly based on design conditions. Therefore, please first locate the required nominal diameter, then check the wall thickness and weight values for the corresponding schedule number according to the applicable standard, ASME B1.20.1 or B1.20.1.
Now, I would like to introduce the transverse internal area and area of metal columns in the pipe data table. The transverse internal area refers to the internal cross-sectional area through which the fluid actually flows when the pipe is cut transversely. On the other hand, the area of metal is the cross-sectional area occupied by the pipe wall itself. As the wall thickness increases, this value grows, and the internal area simultaneously decreases. Since adding these two areas results in the total cross-sectional area based on the outside diameter, you can cross-check them when verifying the table. Also, remember that when the transverse internal area is expressed in square feet, it is equal to the volume in cubic feet per foot of pipe length, which can be used directly for flow rate and volume calculations.
Next, I will introduce the transverse internal area and area of metal columns expressed in square inches. The two area items explained in the previous slide are presented here in square inches, making it convenient for immediate comparison in practice. In particular, the area of metal is the starting value for calculating the weight of a single length of pipe. Even for the same nominal diameter, as the schedule number increases, the wall becomes thicker, increasing the area of metal and decreasing the internal area where the fluid flows. Meanwhile, areas expressed in square inches can be converted to and from square feet by multiplying or dividing by 144, so cross-verifying the two unit notations can help reduce errors when reading the table.
I would like to introduce the area of metal among the horizontal items of the pipe data table. The total cross-section of a pipe is largely divided into two parts: the internal cross-sectional area where the fluid actually flows, and the area of metal occupied by the pipe wall itself. In the table, this area of metal is written in square inches. For the same nominal diameter, as the schedule number increases from STD to XS and XXS, or from 5S to 40S and 80S, the wall thickness increases and the area of metal increases accordingly. Please remember that this area of metal is the basis for calculating the pipe weight per unit length in pounds per foot.
This section covers the horizontal flow of the table, starting from the cross-sectional area in square inches and moving to water weight and inside diameter. Water weight is the weight of water that can fill 1 foot of pipe length, expressed in pounds per foot. The inside diameter is denoted by the symbol D and is written in inches. Knowing this inside diameter D allows you to find the internal cross-sectional area in square inches, and by multiplying that by the density of water, you can calculate the water weight. Ultimately, within one row, the cross-sectional area, water weight, and inside diameter are paired together and used when determining piping capacity.
I would like to introduce the inside diameter column of the pipe data table. The inside diameter, expressed in inches in the table, is denoted by the symbol D. The inside diameter D is the value obtained by subtracting twice the wall thickness from the outside diameter. It is derived by subtracting 2t from the outside diameter, or OD. The unit is inches. For the same nominal diameter, as the schedule number increases, the wall thickness T increases, so the inside diameter D becomes smaller. It is important to verify this inside diameter value accurately, as it is a direct input when calculating flow velocity and pressure drop or performing valve sizing.
Here, we organize the combined headers of the table that lead from the inside diameter in inches to water weight and back to the inside diameter. The inside diameter, D, is in inches, and the water weight is written in pounds per foot for a pipe 1 foot long filled with water. Since the internal cross-sectional area is proportional to the square of the inside diameter, the water weight increases rapidly as the inside diameter, D, increases. Water weight is a converted value obtained by multiplying the internal cross-sectional area by the density of water and the unit length. In practice, the weight of the pipe itself is added to this water weight when designing pipe supports and loads.
This table provides cross-sectional area and weight data for 3 nominal diameters, showing the correlation of physical dimensions according to changes in the schedule number. For example, the inside diameters in the first group range from 1.770 to 1.100 inches, and accordingly, the pipe weight varies from 1.28 to 6.41 pounds per foot. As the schedule number increases, the inside diameter D and internal area tend to decrease while the pipe weight increases. So please check the values in the corresponding row according to your pipe specifications. In particular, since the cross-sectional area expressed in square feet is numerically identical to the volume per foot of pipe length, please keep this in mind when calculating flow rate or volume.
This table is a reference material to ensure data consistency by defining the sources and notation conventions of the pipe data. For example, STD refers to standard pipe and XS refers to extra strong pipe. And for stainless steel, schedules are distinguished by the S suffix, such as 5S or 10S. The remaining detailed figures and standards are organized so that engineers can refer to them directly based on their design conditions. Therefore, please first verify the source standards, such as ASME B1.20.1, and then select and utilize the values that match the required material and wall thickness.
This table is a reference providing wall thickness data based on the nominal diameter of carbon steel, alloy steel, and stainless steel piping. For example, if the nominal pipe size is 1/2 in, you can see that the wall thickness value varies depending on the specification, such as the schedule number or STD. Rather than listing every value, please first verify the material and nominal diameter of the piping you are designing, and then find and apply the wall thickness value for the corresponding schedule number. In particular, stainless steel uses a notation with an S, such as 40S or 80S, so I recommend exercising caution when selecting the specification.
This table is a reference showing the definition of wall thickness, T, and how it changes according to the schedule number. For example, even for the same nominal diameter, the T value for 80S is set larger than for 10S. This serves as a key input value when calculating the inside diameter, D, by subtracting 2 times T from the outside diameter. As the schedule number increases, the pressure rating rises, but the internal flow area narrows, so it is important to select the value that fits your design conditions. For the remaining detailed figures, engineers should first check the nominal diameter and schedule number during actual design, and then find and apply the corresponding T value.